aprender a montarse en el espacio.
Bueno,
Eso, y eso es lo que hacen en los próximos 10 años. Vienen con motos. Y no sé si mira esa idea. Mira esa idea.
Vamos a esperar un minutillo.
estamos cerca de un Kong, ¿no?
Cerca de Hong Kong. Igual,
Perfecto.
No, no, señor, de verdad me recuerdo solo que los hangar en el solo deporte está en la oficina, 200 kilómetros.
bueno, o sea, yo, además que estamos chicos. Y no me sentí fui a caminar subidas. No, hay una sorpresa. Vienen fortísimo. Vienen como coladas.
¿Cómo se llama?
Suban y
De cambiar la velocidad.
Eso sí, gente.
Sí, lo sé, pero en Hong Kong, en Macao, tengo fama, ¿no?
Sí, sí, claro.
Sí, no, el sitio de Hong Kong es como la parte occidental del China. El punto de conexión. No, el punto de conexión.
Okay, I think we're gonna start. Today we have a speaker, Carlos Martínez Ortiz. He is a software engineer and he did the PhD in the United Kingdom, and it's working since 10 years in the Netherlands eScience Center. Today he's going to talk us about software management. So whenever you want, Carlos, it's all yours.
Thank you. Hi, welcome everyone. My name is Carlos Martinez. As Juan said, I work at the Netherlands eScience Center, and I'm going to be talking about software management plans and what are they and what are they useful for research. So I'm going to do something very brave, and I think that you probably all know a lot more about astronomy than I do. But I'm going to start with this image, just because I really like it, and I'm going to ask you guys, does anybody know how this image was made?
By fitting models to the UV plane of the data.
Yes, you're probably more right than I could be. And actually, I watched a really good documentary. I do recommend it, which is called The Edge of All We Know, which is about black holes and about how this image was made. But my favorite take-home message of this is that it was made with software, right? This is not a real telescope. The Event Horizon Telescope is not a physical telescope, but it's a collaboration between the different telescopes, and it's a software telescope, right? So this is a telescope that only exists in software, which is it's a very interesting thing, because it means that software is the tool that we're using to measure something that is in outer space. And this is true for many scientific discoveries that have been made in the last 50 years, that we are more and more using software as our instrument of research. This is true for astronomy, but it's also true in life sciences. So the genome sequences of different viruses, of different proteins in the genomics, it's all done through software, because that's the way we have of understanding the microscopic world. And other sciences like humanities and life sciences, that archaeologists use heavily LiDAR data. So they scan the forest with the airplanes fitted with a LiDAR, and then all the data that they get from the LiDAR, they process it with software, and they discover things that are hidden under the jungle. Climate scientists, of course, everything is software. Climate models are large collections of software packages that talk to one another, try to model the Earth and predict the climate and predict global warming. and if you do anything related to AI, of course, that is all software. So software is a crucial part of the 21st century's academic research, to such extent that the UNESCO considers it a really important thing, and they produced the recommendations for open science a couple of years ago, and in the recommendations for open science, they mentioned open source software as being one of the pillars of open science. So the main point that I'm trying to drive is that the tools that we use for doing science are all based on software these days. And this has always been the case, right? That scientists build the tools that are for their trade. So this is a picture of the first microscope that Anthony van Leeuwenhoek, a Dutch guy, was using 200 years ago to do the first observations of microscopic life. So he was a glass maker, so he was making very small beads of glass, which he used then to observe microscopic life. So he was the first one to observe something which he called small life, a microbe, and he was the first to write about to describe how these microbes look like, these bacteria that he was finding in raindrops in his garden. He was describing how they looked and how they moved and how they lived. So he was both pioneering in the tools that he was building and in the science that he was doing. And so he was building his own tools, collecting his own data for his research. And in a way, at a much larger scale, of course, but the Event Horizon Telescope is a very similar thing, right? We're building the tools for doing the research and for doing our science, with the exception that now we're not polishing very small pieces of glass to create a lens, but we're using software to create our scientific tools. And the downside of these scientific tools is that he had these very small glass beads that if he would drop them, they would fall and they would break. And the same thing is true with software. Software breaks over time. So whenever if somebody reads about the Event Horizon Telescope, they would find that there was a lot of data collected, and there was some software that was used for processing it, and it produced an image. And if in 10 years' time somebody comes and says, oh, that looks really nice, I'll find all their data, download it to my quantum computer laptop, find the same software, and I'll just run it, and it will work, and I can produce the same image that was produced 10 years ago. They would need to do a little bit of detective work maybe to find the software, and what they will probably find is that the software doesn't work anymore. This is true for all types of software, that software breaks over time. If anybody wrote some software in Python 2 and you try to run it with Python 3.12, it's just not going to work. There's going to be lots of errors, lots of exceptions, and it just doesn't work. If you take software that was written 10 years ago and try to run it today, most likely it won't work unless it has been maintained, unless it has been updated to run with the latest version of Python, with the latest version of whatever you're using. Unless it's been taken care of, it will be broken. So reproducibility, of course, is a very important pillar of science. In science, we always want others to be able to reproduce our experiments, to be able to reproduce our research. Otherwise, it's not science. And when software is in the picture for reproducibility, that means that we want if we have a researcher who uses some software to produce some results, today we want that another researcher, or it could be the same researcher, can use the same software to produce comparable results in the future. And that could be another person in 10 years' time, or that could be me tomorrow, or that could be the next PhD student in my research group in next year's time. So we want them to be able to use our software in the future. And likewise, we want to be able to use, we would like to, that they can use different data. So if we have our software and we take some data and to produce some result, we would like somebody else to be able to take a slightly different data set that is of the same type, of the same comparable characteristics, but they will be able to produce a different result. So if we take the analogy of the microscope, Anthony van Leeuwenhoek could take his microscope and look at a raindrop, and he would find some type of microscopic life, but he would look at the yeast, and he would observe something different, because you have the same instrument, but used for different observations, you get different results. Likewise, nowadays, we would have different genome sequences of different species, and we would get different genome sequences, but the genome sequencing software would be the same. So we can use the same tools for different applications, but we want to make sure that the software keeps working for those different observations in the future. So I'm going to talk a little bit of my experience and with software that breaks. And my experience, it's from working at the eScience Center, right? So I'll start by saying, what is it, the eScience Center, and what do we do? So the eScience Center is the National Center of Expertise for Research Software in the Netherlands. It means that the Ministry of Education gives some money to the Funding Council and to the Infrastructure Council. So NWO is our main funding agency, and SURF is our main infrastructure provider. So they run our national supercomputer. And together, they decided that they needed to have like a center of expertise that would allow researchers to use computational resources more efficiently. So a lot of researchers don't necessarily know how to run their code in the supercomputer, and they need some help with that. So we help them use those computational resources. But it's not limited to HPC or to running software in the supercomputer, but also other researchers who may just want to scale their software to run in the cloud, or who may just want to run some analysis in their laptop. We try to help them to be able to develop research software and to accelerate their research by using research software. And we do this in different ways, by collaborating in projects that we fund, by writing software with them, and by office coordination management. So that's by also sharing expertise. So the mission statement of the eScience Center is that we are empowering researchers across all disciplines through innovative research software. So this is very vague management speech, but basically it means that we work across all disciplines. So we work with astronomers, life sciences, linguists, really across all the spectrum of science, from social sciences to engineering. And to use we try to empower them. So we don't necessarily write all the software for them, but we also help them gain the skills that they need to run this software in the future, right? So that, to make it a little bit more concrete, that means that we mainly do two types of activities. So we do collaborative projects and we do sharing of expertise. So collaborative projects, those are research projects in which our engineers collaborate with scientists to produce research software, and we share expertise in different ways, by organizing workshops, trainings in which people can learn how to use the software and the good practices that we develop through our projects. So going back to some of the projects that we work on. So as I said, we work across all domains. So we have lots of projects in life sciences and lots of projects in social sciences and humanities. And we also have some projects in physics and engineering. So the center has existed for about 10 years. And at any given point, we're running anything between 3 and 20 projects. So over the years, I think by now we've run hundreds of projects in which that can range in size. Some of them are 6-month projects, some of them are 3-year projects, but we always try to collaborate with domain experts in trying to solve a scientific problem by using research software. Then in terms of sharing of expertise, this we do by different activities. So we do our training activities, and which means that we do workshops and training programs with scientists, and we mostly based on software carpentry materials and code refinery materials. And these courses are aimed for them to gain the basic skills that they need for doing their research. It can be as simple as learning the basics of how to use Python and how to use version control, but also some more advanced workshops on how to accelerate software using GPUs, or how to use machine learning in a more efficient way. So those are the training activities that we organize. We organize also workshops which are more focused on specific topics. So we have in the past also our technology weeks, in which we have like a group of researchers in a specific domain and that come to work at the eScience Center, and it's like a hackathon, and like a 1-week hackathon to try to solve specific problems using a specific technology. And this could be like GPU technology or natural language processing or machine learning, to try to tackle specific challenges that they have in their domain. And we also develop methodologies, which means because we run all these projects, we learn things that are generic across these projects, like which are the most commonly used licenses for software, which ones work best, what are the single most important things that researchers need to learn about a collaboration in open source, about making software more fair. So we try to also work in developing this methodology of how do you solve problems related to software in a more generic way. So this is where the lessons learned that we learn in the projects, we try to make them transferable to other people. And this is where all the lessons that we've learned about software breaking over time, we try to compile them, find some pain points, common threads, and try to address them in the long term. So how do we prevent software from breaking over time? That's the thing that we're trying to prevent. So what we did to prevent software from breaking over time is that a couple of years ago, we started a working group together with people from NWO, from the main funding agency in the Netherlands. And we started this working group to create guidelines for software management. With the idea that if you manage your software, if you take care of it over time, you can prevent it from degrading. So you can make sure that you have everything you need in place to prevent it from breaking over time. So we had people with different areas of expertise in software from different universities in the Netherlands who were part of the working group and were drafting these initial guidelines. And we also reached out to our sounding board, which had members from national and international organizations who were helping us to proofread our guidelines and to provide input if these would work for them in their research, if these would help their colleagues do their research more efficiently using research software, and if these would help them preserve their software over time. So we had a few rounds of consultation, and we ended up publishing the guidelines in October 2022. So they're a little bit over 2 years ago. But they were the result of a collaborative effort with many people who have lots of expertise in software. And this is the guide that we came up with, the practical guide to software management plan. And the idea is that they're similar to a data management plan, in which basically the idea is that you have a few questions that you answer about your software, and that helps you plan how you will manage it better. And the guidelines that we presented, I'll go a little bit more in detail of these specific guidelines in a minute. But basically, it's to ask you questions about your software. So what does your software do? Who's going to use it? What resources does it need? Who's responsible for it? And answering these type of questions helps you think about your software and plan for your software to be maintained in the long term. And it gives you some clarity about those decisions, so it makes it a little bit more explicit how you're going to address some of these challenges for your software. And ideally, you would have a software management plan as early as possible in your project, so that you can have this clarity early on, and it will avoid problems with your software later on. So a metaphor that I always use about software management plans is that a software management plan is like providing everything. So if you think of your software as a plant, your software management plan is the way to take care of your software, to provide all the water that your software needs to grow to its full potential, right? So you're trying to make sure that your software, it's a small little thing at the beginning, but you want it to grow over time and to develop its full potential. But for that, you need to take care of it, and the software management plan helps you think about how you're going to take care of your software. Okay. So in the software management plan, we had some requirements. Basically, these requirements, I'll go into them in a minute. But there's different categories of requirements. Basically, these requirements are the things that you should be thinking about when you write your software. And in the guidelines, we make a mention about different levels of management for your software, so that not all the software is written in the same way. And that you should take this into account, that all different types of software will have different requirements. And another consideration that is important when reading the guidelines is that a software management plan should be a way for you to do science better, to improve how you're doing your science, and it shouldn't be just like a little bit of bureaucracy that you just have to, a checklist that you just have to comply with, but that it should be a way to do better science. That's the end goal of having a software management plan. So this is an overview of the requirements. I'll try to dig into them a little bit more in detail in a minute, but I just want you to have an overview of them, and to mention that these requirements, we group them in different categories. So we always start from the purpose of your software, which is like this long category here. And the purpose of that's the first thing that you should think about your software. What's the purpose of your software? What problem does it solve? Who's going to be using it, and what for? So that, and I think if you have that clear in your mind, a lot of the other requirements become more easy to address. And then the rest of the requirements, we group them in three different categories. So some requirements that are more in the engineering focus, so that there are more technical things that you can do to make sure your software reaches its full potential. Documentation, which is something that as software developers we don't like to do, but that is very important to document your software. And that you also need to think about who's the intended audience of your documentation, and how they will be reading the documentation, what prior knowledge they have. So that's why we also have different types of documentation. And we have something that we call the project management focus requirements, which are not necessarily technical artifacts that you need to take into account, but that are more other considerations about how you manage your software. Yeah, so as I mentioned, not all software is created equal. So the Australia Research Data Commons, so that they're a similar organization to us, but based in Australia. And they published a couple of years ago their national agenda for research software. And they have this really nice categorization of software, that they also have this notion that not all software, it can mean many different things. And they have this really nice categorization that I really like, and I tend to reuse it quite a lot, that they think of software as falling in 3 categories. And so from analysis code, that this could be just like a small script that you use to process some data to produce a figure for a paper. And then all the way to, you have prototype tools and research software infrastructure. And research software infrastructure would be a data processing pipeline that process all the data coming from your telescope. And that if this pipeline breaks, nobody can do their work for the next week. So you have the 2 extremes of the spectrum, and then you have prototype tools that are everything in between. So I really like that they have these 3 clear categories of software, but I also feel that whenever I end up talking with someone about where your software falls in these categories, we always end up saying, oh yeah, but I think I'm between here and here. So in my mind, this is not 3 categories, but it's like more of a spectrum, that you have some software that is very almost throwaway software that you write once for doing some analysis, and you probably don't need to run it ever again, but it's good if you keep track of what you did. And software that is like that you need to be continuously running, and that needs almost like full-time availability, and then everything in between. And where you sit in that spectrum, maybe it's probably different for every piece of software that you use. So that's why we think of these software management plans as something that you can tailor make for your own software, so that you have all these requirements, and you have to decide from these requirements which ones you're going to pick, and how are you going to then build your software management plan applying these requirements. But you don't need to use everything. You need to use whatever makes most sense for your software. And that is something that nobody can tell you, that you have to decide on your own. These are the things that are useful for my software. So I'll go deep, dive a little bit more into these requirements now. So I'll start, as I said, with the purpose. So this is usually the starting point for any piece of software, that you should think about what problem does it solve, who's going to use it, and what are the advantages and the limitations of my software, right? So you should always try to be aware of what problem does it solve. And if you're trying to do something that is out of scope of your software, maybe you should or adjust the purpose of your software, the scope that you define for your software, or just say, no, this thing that we're trying to do is out of scope for this software. We're not going to do it, and it helps you decide on which features to implement or not to implement. So it also helps you to say, okay, if I'm trying to do this thing that is out of scope for my software, maybe it's better to find another piece of software that does that has that capability that my software doesn't have, instead of trying to force it into your software. You can maybe think, okay, this is outside of the scope of my software. Maybe I need a different tool. So a lot of it of clearly demarking what are the limitations of your software. It also helps you to make sure that you're always using the right tool for the job that you have at hand. Then the engineering focus requirements. So this includes things like version control, packaging, testing, and software engineering quality. And here the questions are always, what version control system are you using? Are you packaging your software? How? If you're testing it, what type of tests do you have? And what type of measures are you using for software engineering quality? So this could be things like linting your software using code coverage, measuring code coverage for your software. And the point of most of these requirements is to make sure that you think about how well engineered is your software, right? So are there things that you can improve in how your software is built that will make it more easier to maintain in the long term and easier for other people to maintain in the future? So of course, I think from this, what I think is the most basic one is version control. As if your software is not under version control, it will be very difficult for other people to find the right version of your software and to make changes to it and make sure that you have a stable version to go back to. And it's also very difficult to share your software with other people because they might modify it and try to contribute back to your project, but if it's not under version control, this is very, very difficult to manage. Packaging testing, it's something that maybe if you just have an analysis script, you don't necessarily need, but if you have something that is closer to production level software, you really want to make it as easy as possible for other people to install your software. And if it's packaged, then they can just install it with one command. It makes it a lot easier to reuse your software in that sense. So it depends. Packaging testing depends on where on the spectrum you are on that software spectrum. And software engineering quality, it's mostly for most prototype tools, is not really necessary. It makes it a little bit better. It makes it nicer to work with software that is very modular and that has very that adheres to code quality standards. But for most analysis scripts and for most shorter scripts, it's not really necessary. It's a nice to have, but it's not a requirement. Documentation, as I mentioned, it depends on the different people who will be using your software. So we listed three different types of documentation: user documentation, developer documentation, and deployment documentation. So this means sometimes there's overlap between these, right? That the developer is the same thing as the user. For just a small analysis script, that might be the case, and then maybe you just need one type of documentation. But if you have something that is more software that works as a service, then maybe you need to know, as the user, I will come to a user interface and I need to know where to click to do the thing that I want to do. And as a developer, I need to know where do I need to make changes in the software to add a new behavior, to add a new feature. And deployment documentation is the in between. If it's software that I will provide as a service, how do I install it and make sure that it's working, even if I'm not going to modify it to add any new features? Again, this is something that maybe not every piece of software requires deployment documentation, but if your software needs that, then you need to make sure that it's properly documented. For the last set of requirements is the project management type of requirements. So these are things that are mostly around your software and not necessarily part of your software, but that are important to make sure that your software works, that others can use your software as well. For example, licensing. Technically, if you can run you can use your software even if it doesn't have a license, right? So who needs a license? If you ask a lawyer, if your software doesn't have a license, other people are not allowed to use it. They cannot use your software unless it has a license. And when it has a license, it depends on what type of license, who is able to use it, and how are they able to use it. And if you have different types of license, so if your software uses some libraries as part of the software, you need to make sure that your libraries are compatible with the license that you're providing for your software. So the software licensing is a topic that gets very complicated very quickly, but that you, as a software developer, you need to at least be aware that software licenses are a topic in itself, and that if you don't know what you're doing, you need to ask someone to advise you at least on how to choose the license that is most suitable for your software. Other of these considerations that are not a requirement but that are important is software citation. So you can use your software and run your software even if nobody is able to cite it, but because we're working in a research environment, citations it's something that is the academic currency, as many people say. So you want people to acknowledge that your software is contributing to science, and then they need to be able to cite your software in the same way that you cite a paper, you are able to cite software. So if you want other people to be able to cite your software, then you need to make sure that you're providing all the information on how your software should be cited. So there are specific file formats that help you. Like the citation file format is a file that helps you contain all that information in one place so that people can find it easily. And that's something that when you create your software, you need to think about, or you need to make sure that it's there if you want your software to be cited. And again, maybe for small analysis scripts that nobody's going to reuse, this is less important. And for infrastructure software that is going to have a lot of users, maybe it becomes a little bit more important. The same thing applies to repositories. So a software repository is a place where you can deposit your software for it to be found by others, and which repository is most logical for your software to be also depends. That's something that you need to think when you're as the developer of your software. So if your software is developed in R, maybe the most logical place for it to be is in CRAN, which is the R archiving package archiving repository. If it's a Python software, maybe it makes more sense for it to be in PyPy. But also maybe if there's a domain-specific repository that makes most sense for your software, maybe you should think about sharing your software in that repository where your potential users are going to be able to find it. So that's also something that you need to consider when you're creating your software. And even though it's not a technical choice in itself. Other things that you need to think about are resources. For example, if your software is a software that runs as a service in a server, you need to think about the long-term preservation of that server. I'm running this server in Amazon. How much is that going to cost me per year in the next 3 years? And if I have more users, that will cost me more hours because they charge me per hour. Do I have a grant which I can pay for, or an organization that had promised me to keep a server online for the next 5 years. So these are the type of considerations that you need to also think about. And what are the risks that are that your software may face, right? And these risks can be in different ways. So if your software runs as a service, is it likely to be hacked? Can you have secure data leaks if your software gets hacked, or does your software work with sensitive data, and then you need to make sure that it has certain compliance with certain security checks. This is maybe not very common for astronomy, but I know people who work in life sciences with medical information. They need to be very strict of where that your software is not sharing any information unintentionally. So depending on the context in which your software is working, in which you're working, your software may present different types of risks, and you need to take as the software developer, you need to take a moment to think about what are the risks that are applicable to your software and how are you going to address them. So those are the different requirements that are here. And then if you take a step back and you think, okay, great, but I know nothing about software licensing. Where do I get started? How can I find some guidance on how to manage my software? So actually, eScience Europe, which is an organization, a collection of funding agencies across Europe, they produce some recommendations on policies for research software, and they recommend funding agencies and research performing organizations to provide some guidance on how to manage software. So how do you manage your software? It's becoming more of a thing at the European level. So where to find guidance for this? It's a very current and very relevant question. One of the resources that we contribute to as the eScience Center is the Turing Way. The Turing Way, it's an online book created by the Turing Institute in the UK, and their guide for reproducible research. And they have different guides, actually, more on the ethical aspects of research, more on the data management aspects of research, but they also have quite a lot of information about research software. So that they have chapters on how to do version control, how to do licensing, how to make research software more citable, how to test your software, how to code review your software. And basically, it's a free online resource that has been created by a very active community of research software engineers, and that they contribute to this book constantly. And if there's anything that you find is lacking, you can also suggest that somebody writes a chapter on a specific topic. So it's a very good place to start if you have any questions about, okay, how do I do this part for my research software? It's a very good place to start. And even if it doesn't have all the information, a lot of the time it just points you to other resources that may give you more information. Another useful resource is that at the eScience Center, we created a software carpentry material, or it's a self-learning material as well. So we organize workshops in which we teach about research software support, but it also can be used as a self-learning material. So this covers a few topics around here. So about research software landscape, about software licenses, publications, citations, version control. And it's basically an online resource that you can use to get started with some of these questions on how to manage your software. And it also has a lot of pointers to other places where you can find more information about this. So for software licenses, it will also point you to websites that have a lot more in-depth information about different types of licenses and how they can be applied and how can they be combined and these type of things. A very hands-on, practical way of get started. A lot of the software that we do at the eScience Center is written in Python. So we created a Python template, which implements a lot of these good practices. So it has different profiles. So you can, when you start, it's using a copier, and when you run this template, you can decide, okay, my software is very minimal. It's the analysis code type of software. I just want to have the bare minimum requirements, and then it will set up your Python project in that way. You can say, well, no, my software, I want it to be like really nice quality, so I want to go with the recommended options, and that will give you almost everything. Or you can say, well, my software is somewhere in between, and I want to make some of these choices. Do I need GitHub integration, not GitHub integration? Do I want to have continuous integration testing or not? Or do I want to use build my documentation using build the docs or not? So you can make all of these choices for your Python project and just get started in that way. We also have another template for Julia, which is also it's under the same GitHub organization, and it has the same idea that you can choose where in the spectrum is your template, and we are in the process of developing a template for R, but yeah, maybe we won't develop it in the end. So that's why I thought I'll just show the Python template, and we have other templates. And actually, this is we started it as a template for internal use at the eScience Center, but we've actually had a few universities in the Netherlands and in the UK who are also interested in using it. They said, well, we are also want to follow similar practices. We also want to have a template. How about we build these together and we can maintain it together, so we don't have to reinvent the wheel every time. And it's more of a community-driven template now. So it's still called eScience Center template, but now it's more of a community effort. That was the last slide that I had. So I don't know how we're doing in time, but I think we have some time.
Okay. You're okay if you want to explain something else?
No, that was that's where what I wanted. I also wanted to have a little bit of a conversation. See if you have any questions. I can point you to other resources as well. If not, feel free to reach out to me at a later point. And yeah.
Okay, thank you very much.
Oh, I see that Mohammed also already has a raised hand.
Yes. Thank you very much, Carlos. A very nice talk. I wanted to know, so right, the SMP, the Science Manager's Software Management Plan, is very, very high level, very to give an outline of every steps and to get people started to think about how they plan to manage the things. I also wanted to know, do you have lower level? Well, you have the template that you showed. But is there like a software, like a certain coding standard that you also recommend? Or is that also part of the pipe, the template, or do you have a separate set of coding standards, lower level?
Okay, that's a very that's a very good question. Let me see. 1 second. But then I'll stop sharing and I'll share again. Okay, so we have at the eScience Center, we have our own guide And this is more so. This is more of a lower level standard of what is it? What are the things that we're trying to do, right? So having like one coding standard is for every project is not going to work because in C you have some different practices than in Python than in R, and every community and every every language and every then. For astronomy and for life sciences, you also have some different ways of sharing your data. So the guide tries to give like some of these opinionated choices, and it has different chapters on like specific practices that we recommend, right? So this is our guide that we use for our engineers and for our project partners. We we recommend others that if they want to use it, they can, and that they can follow our recommendations. But of course, some of these recommendations may or may not work for other organizations. We also try to keep this as lightweight as possible. So whenever possible, we point to the Turing way as okay. We recommend you use version control. We use GitHub because that works for us. But if you want to know more about how to use Git, go to the Turing way, and they have a chapter on version control. Yes. Or there's also this RSQ kit, and they also have a chapter on version control. This RSQ kit, it's a part of the Research Software Quality Toolkit, and that's part of a European project called eVerse. eVerse is the European Virtual Institute for Research Software Engineering Quality. So the idea is that it's a European network on research software quality in which different organizations at the European level are trying to agree on what are the good practices for developing research software. And as part of that, we are developing this research software quality toolkit. So that's a little bit, again, like our guide, it's a bit more hands-on guidance on what are the things that you should consider when you're writing code in a specific language.
Thank you. I have a few other questions, but I'll let others in the room, if they have, go ahead, and then I'll ask after.
Any questions? I have one. When you collaborate with a department or an institute for a project, you enter into the developer team, or you do like an external assessment? How is that relation?
We try that our engineers spend at least part of their time with the research team, with the researchers. So partly because that helps us also build a connection with the team and then understand what are the problems that they're trying to tackle and what are the challenges that they're facing. So I think we usually in our projects we have like a kickoff meeting, and in which we start, and then we have like all the PI and the program manager on our side, and it's a very high level meeting on what is it the project about, what are we going to try to achieve. And then when we actually start the project, our engineer goes and sits with the PhD student, and they spend the day in the room and they drink coffee together. And then it also helps that to the knowledge transfer part, that we understand a little bit more. Oh, so the problem is not actually that you don't know that you're, that you're trying to solve this problem, but also that you want to do it faster. Actually, why don't we, instead of doing it in this language, we do it in this language because that makes it much faster. Oh, okay. So that then sometimes it helps us understand the problem better and find a better solution that was not what the project partner had proposed because they didn't know you could solve the problem in that way. And it also sometimes just helps to share some of these good practices, right? A lot of the time, they don't put project partners don't put on the grant proposal, we need to learn how to use version control system, because they don't know that version control system is a thing, right? And then when we start working with them, it's like, oh, why don't we do this on Git? Why don't we put this on GitHub? Oh, what is GitHub? Oh, here, I'll show you. And because we're working together with the PhD students in that way, we also help them learn a little bit of those things, like with a one-on-one basis. So that works, in my opinion, really well, that we try to work close with the researchers in that way.
And do you also work with foreign institutions or?
We do. So in the project that okay, so our largest part of our funding comes from the Dutch government. So then within that funding, we work with the Dutch universities. But we also participate in European projects like in eVerse. And in these projects, we try to partner up with other international organizations. And we've also had a couple of projects in the past that are similar to our projects, in which we're trying to use a specific tool to work on a specific problem. But that, so I think we had one university in the UK, University of Cambridge, that wanted to work with us because we built a piece of software and they wanted to use exactly that piece of software, but they needed some extra features. And they hired us to work on that project with them. So that was a very focused project in which it was the eScience Center and the University of Cambridge working together in this one piece of software. So we also have some of these constructions that are direct collaborations.
Okay, thank you.
And following Juan's point, so the examples you gave, Carlos, were more in the scope of mentorship, right? What you were describing. So to explain to them how to do this, like with the PhD students, especially. Is that so? And then on the other hand, like with the example of Cambridge, you said that you'd written one software and then they requested technical, let's say, support to expand the features. So the national projects they work with, is it more with the mentorship style, or is it in the more like they just request the software and they have no intention of getting involved in its development? They just like request you to build a software and they just want to use it?
No, it's a bit of both, actually.
Okay.
So we have some in our standard calls. We work together with the researchers, and it depends a little bit on the level of expertise that they have in the research group, right? So sometimes with the projects that are more in humanities and social sciences, they're not necessarily very good coders, right? They don't have this as part of their training. And then we start working with them from the beginning to say, okay, we'll help you get started with Python, and then we'll write some software for you, and then you can learn how to use it, and then we really build some software with them for them. Mm-hmm. In some other projects, like with Astron, with the National Astronomy Institute, they already have some software. They have very capable software engineers in-house, but they're not necessarily experts in using GPUs. Mm-hmm. So they come with us with a very specific problem. It's like, we have this software and we have this pipeline, but we want to speed it up. Can you try? And sometimes after 6 months, it's like, no, this is already as optimized as we could get it, but no, but and then we also learn a lot from these type of projects in which we and sometimes like, oh yeah, actually, if we do it in a different way in the GPU, then you can do it 3 times faster, and then
Yeah.
it works really well. So then these are projects in which we're more building software together with them, right?
Mhm.
And depending on the level of expertise of our partners is how we approach the project. So
Okay. And then what about the final credits? So for example, do you become co-authors in the papers they write? Or do they just acknowledge the eScience Center and not the name of the person who helped from the eScience? What's the policy in that?
so we again, it depends on the project, right? For some,
Okay.
but for the most part, we try to co-author things with our partners. So where if we created the software that then they use for the research, that we try to convince them that they should cite the software as part of the paper. And then that's where when you have citation information in your software, we are the
Yes.
authors of the software, and then
Yes.
the software is cited in the paper.
Exactly. Okay, and the calls were interesting. So how do you what's the so like do you have every 6 months you make calls or 1 year and then that's distributed across the Netherlands for people
Yeah,
to write proposals to?
yeah, exactly. And we have sometimes calls that are more focused on specific domains, and we have the calls that are focused on specific technologies.
Okay.
And we try to keep a balance there to say, okay, now we're going to do a call that is more focused on this domain or on a specific problem. So all our calls are a little bit different every time. And also sometimes we do calls for projects that are a little bit longer, and we also experimented with calls that were a bit shorter, but that was the idea was that in the so that these were part of the technology weeks, that we would have like a short call in which you would work for a very short period in a project, and if there was something successful, then you could apply for a longer project.
Nice.
So it was like more of an exploratory call.
And I don't know, in Spain, I haven't heard about such an institute, right? I don't know. Does anyone in the room know about having a place like this? So across Europe, I'm curious, which other countries have something like the eScience Center? Because as you said, in Australia, I remember I also met someone from Australia who had such an institute. Yeah, I'd like to know across Europe where they have. So maybe we can start the discussion for Spain to have such a place.
Absolutely. So it's quite having like a national institute like the eScience Center is quite uncommon. I know in Norway they have a similar institute, but it's a little bit more distributed in a way, so that they're not like one institute with a lot of software engineers, but they're more like a virtual institute in which there's 3 groups in different universities, and they have like a pool of engineers between them, and then they're each based at a different university, but they work together a lot.
Okay.
And I know, so what my boss actually, he went to Germany a few weeks ago, maybe a couple of months ago, because in Germany they were interested in starting a similar institute, and he had some conversations with people from the German funding agency to say, okay, how does the eScience Center work? How is it structured? How is it funded? And how can we start something similar in Germany? And I know in the UK, there's quite a lot of local RSE groups. So the University of Manchester, for example, and I think Leeds, they have like a RSE group that is a central RSE group, so Research Software Engineering group, that helps other departments. and they're not based at any faculty, but they're supporting the faculties with their research software. So that's like a similar approach to what we do, but we do it at the national level and they do it at the university level.
Great, thank you.
So if there's interested for doing something like this in Spain, it would be great to see that, and if we can support you in any way by talking to people to see how this works in the Netherlands and how it could work in Spain, we would be very happy to help with that.
Yes, that would be great. Yeah, we'll get the discussion started, hopefully sometime. Maybe we can start with, because we already have a big, our institute, as I explained before, we have a big telescope that is conducting a big survey, and it's an international collaboration with many institutes. So maybe we can start it as like the UK model on a smaller scale, and then like for our specific survey. And then ask for grants, like get some research software engineers to help the users of our data across Spain and our collaborators, and then grow from there maybe. Of course, it's a long-term thing, but yeah.
With many of these
It's a
things,
very nice model. It's a very nice model to have in mind that like in 10 years, in 15 years, in 20 years, we can reach something like that on a large scale.
Yeah, absolutely.
Yeah.
Okay, thank you very much, Carlos, for the very nice talk and the conversation.
Yes, thank you.
Thank you for having me, and it's been a pleasure, and hopefully we'll meet again in the future.
Yes.
You're very welcome to visit us whenever you want.
Thank you.
Okay.
Have a good day. Bye-bye.
Bye.
Bye.